Hi, everybody, and welcome to today's installment of the Spectral Geometry in the Clouds seminar. Today, we have the pleasure of having Mickaël Nahon from the Max Planck Institute for Mathematics and the Sciences, who will speak to us about sharp stability of higher order Dirichlet eigenvalues. As usual, if you have questions during the talk, you can either unmute yourself and ask it directly or ask the question in chat and we will relay it to the speaker. Mickaël, the floor is yours.
So first, thank you for the invitation to present this here. And yes, I'm going to present the stability of higher order Dirichlet eigenvalues. This is a current project with Dorine Bucur, Jimmy Lambolet, and Raphaël Prunier. So the main plan is this. First, I will only present results, and then I will move on to explaining a bit how the proof of the results work, and then some applications. Okay. First, let me introduce just the notation that I think many of you are familiar with. For the notation, I will always work in the Euclidean space Rn, where n is larger than 2. B is a unit ball. The set A of admissible set is every open set of measure the same as the ball, with no particular topological constraints. Lambda k is the case eigenvalue of the Laplacian with Dirichlet boundary conditions. And I call UK the normalized eigenfunction. I will also use a lot the torsion, the torsional rigidity that I will just call the torsion, T of omega, which you can define either with this energy here or as some kind of quotient. So 1 over the torsion is basically very similar to lambda 1. And typically the torsion function is a function for which this maximum is reached. And it verifies a very simple elliptic equation like this. And I remind that the two basic inequalities for lambda 1 and the torsion are the Faber-Kran inequality, that lambda 1 is minimal on the ball, and the Savenot inequality, that the torsion is maximal on the ball. The question I'm looking at is the following. Suppose that the first eigenfrequency of your set, omega, which has the same measure as the ball, is close to the one of the ball. Then can you say in some quantitative sense whether the case eigenfrequency, so the case eigenvalue, is close to the one of the ball? So first, let me explain a bit what happens for like small perturbation and smooth perturbation of the ball to see what we can expect at best. So if I take like a vector field zeta and I look at the perturbation of the ball by this vector field zeta, then in general, you have like a directional derivative for the eigenvalue. It may not be the same on both sides, but you have a directional derivative that I write formally like this. Lambda k prime of B applied to zeta is the derivative of the perturbation by T zeta. And I can consider this for vector field zeta that do not change the volume of the ball, at least at order 1, to see what happens. And when you do this, you see that you have two kinds of eigenvalues on the ball. You have simple eigenvalues, lambda k, for which, so if lambda k is simple, the eigenfunction is stable by rotation. So in particular, it's a radial eigenfunction. And here, the derivative of lambda k is given by just this formula here. So you have the normal part of zeta, and you have grad of uk square, which is a constant here. So this is 0. And this means in general that the ball is a critical point for lambda k in this informal sense. On the contrary, when lambda k is multiple, in general, the differential is not 0. You can't find vector fields that change the differential. And now, to be a little finer with lambda 1, we can say that if you remove any vector field that is not interesting, meaning vector fields that just do rotation of the ball or translation, meaning that if you suppose that the barycenter or some other normalization of your ball is fixed in the middle and your vector field is normal, so you have no rotation, then lambda 1 is not only a critical point, it's also a non-degenerate critical point in the sense that you have like a coercivity. So you know that it's a strict minimum with a very quantified lower bound like this. So you see that lambda 1 of bit zeta is larger than lambda 1 of B plus the h1/2 norm of zeta square. And you can find this, for example, in Brasco, De Filippis, and Vejiškov. And so if you can make a drawing of what the situation looks like, so if you imagine that sets the horizontal axis is sets omega that I put on just one dimension, and on vertical axis I follow eigenvalues, then lambda 1 would look something like this, with a non-degenerate critical point, with a non-degenerate critical point in the middle. Lambda 2, lambda 3, so into the they cross here, and we follow lambda 2, which is the lower part, and lambda 3 is the upper part. Same for lambda 4, lambda 5, and then you have lambda 6 that is simple. And so you see here that if you want to measure the deviation of lambda k with lambda k of omega with lambda k of the ball, then when lambda k of the ball is simple, so for lambda 6, the best you might expect is that the deviation of lambda 6 is like the deviation of lambda 1. So you have a linear band. Whereas if lambda k is degenerate, then the best you can hope is, because here the deviation is quadratic and here the deviation is linear, you might expect a square root band like this. So now I can cite a few known results around this. So really like the few known quantitative results around this problem. There is one of Bertrand and Colbois in 2005, where they use like capacity estimate to prove that so when lambda 1 of the ball is not too large, otherwise this inequality is wrong, but when lambda 1 of the ball is bounded, let's say, then the difference of lambda k is bounded by the difference of lambda 1 power an exponent. That depends on the dimension. You have a more recent paper of Mazzoleni and Pratelli, where they say, so they have exponents that depend on the dimension and whether you take an upper bound or lower bound. But more or less, you have an exponent like 1/12 minus epsilon for an arbitrarily small epsilon, for any arbitrarily small epsilon. And also, I can cite a result that does not say the same thing, but that is closely related, which is the quantitative Faber-Kran inequality of Brasco, De Filippis, and Vejiškov. Because in a way, they say that when lambda 1 of the omega is close, the deviation of lambda 1 is small, then your set is close to a ball. The issue with this result, in our case, is that the distance between set is in L1 sense, and this is really not enough to say that the eigenvalues themselves converge, because you can take a set and you remove a line in the middle, for example. So now let me present the first result. The first is for degenerate eigenvalue. So we say that there exists a constant, Cn, such that the deviation of lambda k is always bounded by the square root of the deviation of lambda 1, with some constant in front. And so you see this inequality is actually not very good when lambda 1 of omega is large, but when lambda 1 of omega is small, it gives a new estimate. And so something that I will use in all the rest is, actually, I will not look directly at this functional. I will look instead at the deviation of the torsion. Because due to the inequality that was proved by Kohler-Jobin, you know that this quantity here, so you have a multiplication of a term that is maximal on the ball and a term that is minimal on the ball, but with the right exponent, there is a competition between the two, and it is still minimal on the ball. And as a consequence of this, the deviation of torsion is bounded by the deviation of lambda 1. So what we prove is actually that the difference of lambda k is bounded by the deviation of the torsion. And then we apply this inequality and we get this one. And so this inequality is sharp when you have eigenvalue lambda k that is degenerate. When lambda k is simple, we have instead a linear band. So here I suppose that lambda k of the ball is simple, then there is some constant such that the deviation of lambda k is bounded by the deviation of lambda 1. And to be slightly more explicit, the constant Cnk here is like semi-explicit, like it's equal to a constant Cn that is not explicit times the polynomial in k over what I call the spectral gap, which is like the distance in the spectrum of the ball between lambda k and the nearest neighbor. Okay, and as I said earlier, so we actually prove a slightly different version with the deviation of the torsion instead. Now we have a third result, a third linear band like this, because, so let me just go back very quickly. As you can see here, lambda 2 is like this and lambda 3 is like this, but when you see the two together, when you look at the symmetric function of the two, it is still a smooth function even near the ball. And like the sum of the two eigenvalues, or the product, is still has a critical point at the ball, because like the derivative on both sides cancel each other. And so even if individually you don't have a linear estimate, you get a sharp band for a group or a cluster of eigenvalues. So the form that it takes is that you take K and L such that you have a whole group of eigenvalues of the ball, lambda K to lambda L. So for example, in 2D, they are always of multiplicity 2. Then the sum of lambda I minus of omega minus the sum of lambda I of B is bounded linearly by the deviation of lambda 1, and with a very similar constant in front. So, for example, in 2D, you can say that the arithmetic mean of lambda 2 and lambda 3 is the deviation of this quantity is linearly bounded by the deviation of lambda 1. And you can even weaken this inequality a bit to see this as like a linear band, but only on one side of lambda k. So for example, this directly implies two inequality, that the difference of lambda 2, but with no absolute values around, is bounded by the difference of lambda 1, and the opposite difference of lambda 3 is bounded like this. So for example, the first inequality is actually consequence of a result of Ashbo and Ben-Gurion that says that the ratio lambda 2 over lambda 1 is maximal on the ball, because you can directly transform it into an inequality like this, and the bottom one, not sure. Okay, so these are the main results. Okay, and as I said, we prove it for the difference of torsion instead. Okay, so first, I will say a few words about the square root bound, which is the 2 or 3 slides. So the square root bounds has a few ingredients. Basically, we have 3 main inequalities that we will use. The first one is a lemma from Dorin that says that if you take, so instead of comparing 2 sets that have the same measure, if you take 2 sets that are included in one another, U and V, then you can compare the eigenvalue by the difference of torsion. And more precisely, you look at 1 over lambda k. This is like the case eigenvalue of the resolvent. So starting from the top, when you start counting the eigenvalues from the top. And this difference of eigenvalue is bounded by the difference of resolvent, which, when you have one domain inside the other, is just bounded by the difference of torsion. The second lemma is like, want to understand what happens when you have a domain omega that is close to a ball, and you compare it with omega intersected with the ball. And you want to say that the torsion of omega intersected with the ball is not too small. When when the symmetric difference is small, the torsion does not change too much. And this is basically by choosing a good test function for this torsion here. We can say that this difference is bounded by symmetric difference. And then finally, there is a quantitative Faber-Hahn inequality that says that up to doing a good translation on either the ball or omega, this symmetric difference is bounded by the square root of the deviation of lambda 1. So actually here, you can put the deviation of lambda 1 or the torsion. They prove it for both. And once you have this, then you basically decompose your inequality by putting the eigenvalues of omega intersected with the ball in the middle. I see a question in the chat. Did I tell what Pascal A is Yes, sorry. The A is a set of every open set of same measure as the ball, so of measure pi in 2D, for example. Okay, and so the difference of lambda k is so you bound it by this, and then on both sides you apply the inequality for a nested set. So you can estimate this by the difference of torsion. And then on one hand, when you rearrange this, you have the deviation of the torsion. So this one is good, it's what we want. On the other hand, you have this difference. And this one I just said is bounded by the symmetric difference, by the L1 distance. And now it's bounded by the L1 distance, but when you place them properly, you can apply the quantitative Faber-Cahn inequality and you get the square root of the difference of lambda 1 or the torsion. It works the same here. And that's all. For the quadratic, for the square root bound, this is enough. So now, for the rest of the presentation, I will talk about the linear bound. And I will mostly explain what happened for lambda k that is simple, not for the cluster, because it's a bit more complicated, but it's essentially the same ideas. But okay, the first observation is the following one. So suppose that lambda k of the ball is simple. You take omega that has same measure as the ball, and you want to prove the first inequality for some large enough C and K. And then you put all the omega on one side, all the ball on the other side. So this is like saying that 1 over the torsion, so this is like lambda 1 basically, plus a small plus or minus a small constant times lambda k is larger than the same quantity on the ball. So in a way, we can rephrase this problem as saying, can we prove that 1 over t omega plus delta lambda k of omega is minimal on the ball when delta is small enough? So, and first we can try to see why it should work, is that we know that 1 over t, so as I said, which is like lambda 1, it has a unique minimizer at the ball, and it has some kind of coercivity property. So it's non-degenerate near the ball. Whereas lambda k, it has a critical point at the ball because lambda k is simple. And so basically we have a function like x squared that we perturb by a function that has 0 derivative in 0. So at least we expect that the ball is still a local minimizer of this. And then the challenge is to prove that it's a global minimizer. So, okay, so this is the plan of proof. The plan of proof is, so in every step, you can add when delta is small enough every time. But basically, when delta is small enough, we first prove that there is a minimizer, but among a less regular kind of set, so among quasi-open set. Then we prove that this minimizer is actually an open set, and like the torsion function and eigenfunctions on it are Lipschitz and have some kind of non-degeneracy property. Then we say that the minimizer omega is close to the ball in increasingly stronger sense. So we have first L1, then Hausdorff sense, and so on, until we have that it's close to the ball in a C2 gamma sense, so in a C3 sense, basically. And finally, we say that, so as I said earlier, this functional, when you are only in a very smooth neighborhood of the ball, in a very small neighborhood of the ball too, it is still minimal at the ball. And so you see that there exists a minimizer omega. We prove that omega is very close to the ball. And then we proved that very close to the ball, the minimizer has to be the ball. So the conclusion is that when delta is small enough, the minimizer of this functional is exactly the ball. Okay, so I will give a few details for each step, more or less. The first one, basically the challenge is to prove that homogenization phenomena cannot happen. So to prove that there exists a minimizer, where we do like a classical way, we consider a sequence omega p, a minimizing sequence. So omega p are like smooth sets. And we want to prove that it converges to a minimizer. The issue is that a sequence of domain like this it might not converge to a minimizer at all. It might converge to like a capacitary measure, so in a relaxed setting. So what happens, so basically, is that if you have a sequence of set like this, omega epsilon, with a lot of very small holes, so like you have holes that are spaced by epsilon on each side, and the size of the hole is also given by some function like this, where rho is like a smooth positive function in omega, then this sequence of domain will not actually approach the eigenvalue problem on omega, but it will approach a modified eigenvalue problem. So where you have like the eigenvalue equation, but with additional rho u here. And okay, so this kind of measure, it can be a consequence of homogenization process, or just that your sequence, your minimizing sequence, behaves very badly. And so we want to prove that this does not happen. And to be a bit more precise, so when you have a measure mu, so we are going to like replace the domain with a measure. And typically when you have a nice domain, the measure is infinite outside of the domain and zero in the domain. So it's like a potential that is zero where the domain is. But for any measure mu, that is a capacitary measure, this is a technical detail, we can define the torsion and the eigenvalue in a way where basically you replace grad u square by grad u square plus u square d mu. So you add this additional term on top. And we look at admissible measures, so measure whose domain has the same measure as the ball. Okay, and as I said, an open set omega, it corresponds to a measure that is either 0 or infinity. And the first step is that we prove that there exists a capacitary measure that minimizes our functional. The second step, so this is by concentration compactness method more or less. The second step is showing that the measure has this form here. And basically, a measure, it corresponds to a domain, as I said, when it is either 0 or infinity. And for example, the measure mu is like this when 1 plus t mu is equal to mu for every t, because 1 plus t times 0 is 0, and 1 plus t times infinity is infinity. And so what we do is we replace mu by 1 plus t mu, so it corresponds to like changing a bit the size of the hole asymptotically. And when you derivate this, so you expect to find 0 when mu is a minimizer, but you find this quantity here. So a constant times the torsion function square plus delta, the small parameter delta, times the eigenfunction square. And then we know that there is like a universal estimate that says that the eigenfunction is always bounded by the torsion function. So the ratio of the two is always bounded by a universal constant. And so when delta is small enough, you see that this term, it gets absorbed in the first one. So you get that, you get this equality, that the torsion function is 0 everywhere where mu is non-zero, is not infinity, basically. And so as a consequence, we get that mu is either infinity or 0, and that the domain of mu, which is basically the place where the torsion function is positive, for now it's not an open set, it will be right after. For now it's just a quasi-open set. Okay. So now this one I will not detail, but basically once we have a minimizer, a quasi-open minimizer, we can say that the torsion function is Lipschitz and it's non-degenerate. So being Lipschitz, it directly means that the domain of positivity of this function is an open set because it's continuous. The second condition basically tells you that around every point of the support of W, it grows at least linearly. It cannot be too flat. And the consequence of this one is typically that omega has finite perimeter, but this is not useful for us here. And as a consequence, we also get that the eigenfunctions are Lipschitz. And so now we have a minimizer among open sets, and we can start to see what we can say about the optimal problem. Because when we have like an optimal domain, we can hope to have some kind of overdeterminate condition, like some kind of additional condition that comes from doing a shape derivative of the domain. So first, the idea is to say that if everything is smooth, so if the domain is completely C2, C3, something, then we can do a shape derivative. So as I was doing earlier with the ball, you take a vector field and you make the domain follow this vector field for a short time, and you see what happened. And you derivate your quantities, and you see that the torsion function W and UK will verify this equation. So the first line is just the interior equation. The second is just the boundary condition, and then you have an additional boundary condition that the gradient square of W plus a small constant times the gradient square of UK is equal to Q, where Q is a constant. Okay, and d nu I call the inward derivative. So, for example, if we had taken delta equals 0, so a case where we expect to find the ball as a minimizer, if we had taken delta equals 0, so this term disappears, and Q is actually equal to 1 over n squared. So we find that we have a torsion function that is like that is 0 on the boundary of the domain, and that has constant gradients. The norm of the gradient is constant. And this is a theorem of Serine that if you have this, then automatically your domain is the ball. So here what we have is pretty close, because we have that the derivative of the gradient is 1 over n plus something small. And so there are like quantitative version of the Serine theorem that say that under this kind of hypothesis, your domain omega is a perturbation of the ball. So the problem is here is that the sense in which it's a perturbation of the ball is not clear here, so we don't really use this. Okay, and as I said, this equation we get assuming that that the boundary of the domain is smooth, but this is actually not a problem, because so this one is maybe more a technical issue, but this equation is actually valid at every contact point of the boundary, where by contact point, I mean that you have your boundary and you look at points that are touched by a ball on either from the interior of the domain or the exterior of the domain. So, okay, you say that X has a contact sphere if you have a ball either fully included in the domain or the complementary that C with X on the boundary on the sphere, on the boundary of that ball. Where nu here typically is the inward normal vector, but it might not be the unique inward normal vector. And what we say is that if you take a contact point, a point with a contact sphere, then actually W and UK, they have a gradient. So like when you zoom in, you see that they are both linear, they have a first order development. The norm of the gradient are respectively alpha and beta, and they verify the previous relation. And this will be enough for our needs, because this is more or less, so we say that the previous relation here is verified in the viscosity sense. So once we have this is closer to, so this is very close to the Alt-Caffarelli problem, which is typically the same thing, but when you have only one function. Here it's a vectorial version of Alt-Caffarelli problem, which has been studied in some settings. So for example, when delta is positive, because I remind that delta is small parameter, but it can be positive or negative. When delta is positive, this has been studied in a paper of Krivensov and Lin of 2019, I think. And so they have some regularity theory for this. Like they can prove that if you have a minimizer of this that is flat enough, that is between two hyperplanes, then it's actually a smooth function. The boundary of omega is given by the graph of a smooth function. For delta negative, something has actually been done, which is much more recent. It's by Mickaël Nahon and Velishkov from 2021, I think. Because basically, when you make a change of variable, you look at the overline omega, W and underline W, so that are just perturbation of W. You see that the product of these two things is W squared minus delta plus delta UK squared, basically. And the product of these two, they verify some similar equation like this, where you have elliptic equation inside, Dirichlet condition on the boundary and the product of the two gradients on the boundary that is constant. And this one has been studied by Mickaël, Nahon, and Velichkov, and they also have like C1 alpha regularity, meaning that the minimizer are going to be C1 alpha. So let me just explain what happens for a cluster. So when we have a minimizer of the cluster functional, then we have a certain number of functions here, and we have an additional boundary condition, which is very similar. So you have the gradient of W square plus delta times the sum of the gradient of the eigenfunction square. That is a constant. And when delta is positive, this is still in the setting of Krivenshoff-Handlin. When delta is negative, it is not in the setting of Mickaël, Nahon, and Velichkov, so we need to redo all the regularity theory, more or less, but in a very similar way. And so let me explain a bit like how this kind of thing is done. So typically, we try to look at what we call flat solution. So flat solution is when you take like a point on the boundary of your domain, you zoom in and you see that your domain is almost flat. The boundary is almost flat. And so typically, instead of looking at the domain, we prefer to look at the torsion function. It gives us more information. And basically, a function W, we say that it's epsilon flat in the direction of in the direction E in the ball of radius R. When so the first condition is just to say that in the middle of your ball you have a point of the boundary. The second condition is just to say that your function is almost harmonic on its support, so it's either 0 or something almost harmonic like this. And the third one is to say that W is very close to a linear function in the direction of E. So it's close to x times E plus A, is between x times E plus A and x times E plus B, where A and B are close, like epsilon close. So here I made a drawing. So imagine for a ball of radius 1, the domain, which is in blue here, the boundary of the domain is between two lines of distance epsilon, two parallel lines of distance epsilon. And so the first, so we follow more or less the procedure of De Silva to prove regularity. The first step is saying that if you have something that is flat in a ball of fixed radius, then in a smaller ball, for example, you halve the radius, in a smaller ball, it is like it oscillates slightly less, in the sense that you're going to say that you are in either one of these situations where so the blue line, which is the boundary of your set, is either below this red line or above this one. So here in this situation, we verify both, but we could verify only one of the two. Where basically this red line is, gives you that the oscillation inside the ball of radius 1/2 is bounded by 1 minus nu, which is like a universal constant smaller than 1, times the oscillation on the ball of radius 1. And in our case, we say that this kind of thing is verified when all of the perturbation of the torsion function, so torsion function plus or minus a small constant times the eigenfunction, when these are flat in a certain direction, then in the same direction, it is still a bit flat on a smaller ball. And this kind of estimate is not actually enough to say that the boundary is smooth, because this is not something you can iterate. Like you cannot zoom in on the smaller ball inside and then apply this again infinitely. Because you see, 1 minus nu typically is going to be very close to 1. So 2 times 1 minus nu is going to be larger than 1. Meaning that even if you are epsilon flat in the ball of radius r, in the ball of radius r over 2, you are a little less than epsilon flat. Well, you are 2 epsilon flat, more or less. And so this you cannot apply indefinitely. But it's enough to get some kind of compactness for a sequence of minimizer, which gives the second regularity, which is improvement of flatness, where you say that under the same hypothesis that you are epsilon flat, then on a smaller ball, by changing a bit the direction, you are 1 minus nu epsilon flat. So the nu here is not the same constant as just before, it's just a universal constant. And this one, you see, you can iterate actually. Okay, so this one more or less is obtained by compactness using the previous one. But this one you can iterate, like you can do it as much as you want when you zoom in, because you get flatter and flatter. And this so basically imply that when you have a minimizer that is flat in a ball, then in a slightly smaller ball, it is a smooth graph. So it is a C1 gamma graph, where gamma depends on the constant nu here. Because you can see that the fact that we can iterate this procedure geometrically means exactly that we have C1 gamma regularity. And okay, so we can do this kind of procedure to say that when your domain is flat near some point, then it's actually smooth inside. The problem is that there might still exist places where the domain has corners or things like this. So now I will explain why it is not the case. So the regularity result, you can state it like this. You say that you take any small eta, you say that there exists some positive number delta, that when it is small enough, then when you look at your minimizer, t minus 1 plus delta lambda k, where this delta here, it can be positive or negative, the domain, the optimal domain for this is a very small perturbation of the ball. So it's a perturbation of the ball by a function that is small in C2 gamma norm, where constant eta is here and here. So first we say that the minimizer, they approach the ball in the L1 sense. So this is basically the quantitative Faber-Cran inequality. Then we say that they approach in Hausdorff distance, so the boundary approach in Hausdorff distance. And this is basically just using the regularity, the Lipschitz and non-degeneracy estimate on the torsion. Then with the previous stuff I presented, so we can say that it's now the graph of a C1 gamma function on the ball. And then by something that I will not explain here, we can then iterate to get higher and higher regularity. And for us, we'll just stop at C2 gamma because this is enough for us. But here we could put like CK for NK. So now we know that as delta gets smaller, our minimizer are smaller and smaller perturbation of the ball. And well, finally, we just need to use the local minimality of the ball. And this one can be explained like this. So on the top, so when I take omega that is, so BH was, as I said earlier, like BH is this set right here. So it's a perturbation of the ball by a function h, by a graph h on the boundary of the ball. You say that when omega is equal to BH, when h is small enough, and you normalized to avoid like having rotations and translation of omega, then you have a coercivity of the torsion in term of h1/2 norm. And on the contrary, the deviation of lambda k is controlled by the h1/2 norm. And so now you take omega that is a minimizer. So you take any omega like this, and you can just apply this to inequality to say that the energy of this is larger than the energy of the ball, plus something, plus a constant minus delta times another constant times the norm of h. And so when delta is small enough, this is positive. And so h has to be 0, like h has to be 0 if we want omega to be a minimizer. And so, okay. And so in the end, what we get is that by the previous slide, we know that there is a minimizer that is an arbitrarily small perturbation of the ball as delta goes to 0. And then when delta is small enough, the ball is a minimizer in a neighborhood that does not depend on delta. Okay, so now let me give a few application and open questions linked to this. The first one is for linked to the Kohler-Jobin inequality. Because so the Kohler-Jobin inequality, I remind, is the fact that when you look at this product, so the torsion power to the power something times lambda 1, you have a competition between the two, one that is maximal on the ball, one that is minimal, and it is the eigenvalue that wins. So this is minimal on the ball. And what we get here, when we look at 1 over the torsion minus delta, a small positive delta times lambda 1, we get like an opposite inequality. So we can state it in two different ways that I put here. The first one is we can say that there are two universal constants, Cn, such that for any set in A, so that has same measure as the ball, the deviation of the torsion and the deviation of lambda 1 are equivalent. So the upper bound is it just comes from the Kohler-Jobin inequality, and the lower bound is nu. And you can state it in a different way, saying that when you take a large enough exponent and you look at this functional here, so it's a variation of this one, then for some large enough p, this is maximal on the ball. And then for any small large enough p, this is maximal on the ball. Okay, so this is the first consequence. Another remark is that we could have looked at different symmetric functions. Like we looked at the sum, but there isn't anything particular about the sum compared to the geometric mean, for example. But this, we could have looked at any symmetric function. It works the same. Basically, if you take any function f from lambda 1 to lambda k, where lambda k and lambda k plus 1 are separated, and you suppose that f is symmetric in its variable when these variables are degenerate on the ball, meaning that it's symmetric in I and g, where lambda I of the ball equal lambda g of the ball, then you have the same kind of stability on f. Also, you suppose that f is sublinear because otherwise, like if you take like lambda 6 square, for example, it verifies this, but you can get higher and higher values. But you suppose that f is sublinear, then you have this kind of stability. So here is an example of an application. Instead of looking at sum, we could have looked at multiplication and ratio of eigenvalues. And so now I can give an open problem, which is what about like more general functions of eigenvalues? What if we want to say something about like the trace of the heat kernel or the zeta function associated to the eigenvalues or something else, or some kind of asymptotic stability? Then, so basically the proof of the previous theorem is we take our two results, which are these two ones. So the square root estimate and the linear estimate for a cluster of eigenvalue, and we inject them in the symmetric function. The problem here is that these functions, they depend on an infinite number of eigenvalues. So the constants that we have in front here, they start to actually matter. So for the square root bound, we have a constant that is polynomial in k. So typically for this one with the exponential decay, it's going to be nice. We're going to get like a square root stability. However, when we want to use the linear stability, we have the spectral gap g of k on the denominator here, which I remind is defined as a distance between lambda k and the nearest eigenvalue. So even if lambda k is degenerate, you look at the distance with the nearest eigenvalue that is not lambda k. And we don't know any reasonable lower bound on g of k. And so I can leave this open question: is there some lower estimate of g of k by, for example, a polynomial function? So this question is actually very linked, I think, to number theory problem, because if you, instead of looking at the ball, you look at a rectangle, when you look at a rectangle with algebraic ratio, then this property is going to be true. However, when you look at a ball where the ratio is like what's called a Liouville number, so it's a Trace-Nuttall number that has a special property that it's very well approximated by rational, then this property is going to be wrong. We need to put a much smaller function here. And so the question is whether the eigenvalues of the ball verify this. So typically the eigenvalues of the ball, they are given by zeros of Bessel function. So the square of zeros of Bessel function. So I write them like this, where p and k are index. Basically, g of mu k is a case positive zero of the mu Bessel function, which basically look like sinusoid that decay at infinity. So there's an hypothesis that was proved by Bourget, something called Bourget hypothesis, but it's a theorem that was proved by Siegel that says that when you take two zeros that corresponds to this eigenvalue of the ball, basically, for different Bessel function, then they cannot coincide, meaning that you cannot have like a radial eigenvalue and a non-radial eigenvalue that coincide. And the question that so I put our hypothesis because I don't know if it appears somewhere else, is whether you can have a quantitative version of this. And this would allow for like a more linear like a linear stability for like zeta function of lambda k or trace of the heat kernel. And okay, thank you for your attention. I think I will stop here.
Thank you very much for this nice talk. We now have time for questions, so please just unmute yourself or write in the chat, something like that.
So I have a question / maybe comment about the last open problem you've mentioned.
Yeah.
Or this hypothesis actually. So in March this year, there's been this paper by David Scher, who talks about joint asymptotic expansions for Bessel functions and find quite precise uniform asymptotics in the parameters for the zeros of Bessel functions. Did you try looking at this paper and trying to see if you can extract this hypothesis out of it?
I have to check again because I think I recall that it was like for a fixed Bessel function, like G mu, you have an asymptotic of the zeros, something like this, right?
I mean, so that's part of what's done in that paper, but the whole point is that there is a uniformity in the parameters, and there's a notion of separating those zeros well enough, and this is actually what has been used by himself with Michael Levitin and Josef Polterovich to prove the Polya conjecture for the disk, where you do have to work with all Bessel functions together. So in a way, I mean, to have a good first step towards that hypothesis or proving something of this type, I would look into these two papers from last March.
No, that's interesting. Yeah, because okay, I have to check again. I think the issue was mostly that it's for like fixed Bessel function, but we want to know what happened for very different index Bessel function. But yeah, I will have to check again. Yeah.
Thank you. There's a question in the chat by Chris Judge who says, is there a proof of Bourget's hypothesis that does not follow Siegel's method?
I think there was one, but in the end it comes down to knowing that the zeros are transcendental in some sense, I think. So I don't know another one. Maybe there are, but I don't know another one.
Thank you. Are there any other comments or questions? I have a simple, very naive one to know if any of this would work for different boundary conditions. Boundary conditions other than Dirichlet.
Oh. So yeah, this is a good question because, for example, for Neumann boundary condition, you might want to look at the maximization of mu1, for example. So the first difference is that the ball is not a critical point because mu1 becomes degenerate. So you could look at the maximization of or the minimization of 1 over mu1 plus 1 over mu2. So not only this, we don't know in general, like without any topological constraint, that it's minimal on the ball, but this one, it has a critical point at the ball. Then, okay, probably it's possible to say by shape derivatives that if you have some kind of coercivity, I don't know if it has been checked, but if you have some kind of coercivity, so coercivity as we had here, for example, for the torsion, for some different norm, then you can say that when you perturb the functional, it's still going to be locally, like the ball is still going to be a local optimizer. Now, if you want to do the same method, the issue is with the regularity, because so if you want to say that if you want to consider like a optimizer for some spectral functional with Neumann boundary condition, we need to know that this kind of thing exists. As far as I know, there isn't a very general theory for this, and we need to have like regularity theory, so similar to regularity theory like this. And this, I think, is also a problem for Neumann boundary condition. So I'm not saying no, but it would be interesting to look here.
Thank you, Mickaël. Anyone else wants to go with a final comment or question? If not, let's thank Mickaël, again. Thank you very much for this very nice talk. And we will meet again next week for the last talk this semester by Mickaël who will speak about growth and divisor of complexified or cycle eigenfunctions. See you all next week. Thank you very much.
Thank you very much.
Thanks a lot, Mickaël, for the talk. It was very interesting.